All right, so today we're going to make Taylor series, and we'll start by doing it the long way, and then just once we have some series established for sine, cosine, and e to the x, then we can just start to reuse them instead of having to build them every time with the formula. So we'll review the formula we used for Taylor polynomials, and that was f of x, or it was p of x, pn of x, but we started with, if it's centered at 0, we do the function at 0, then we do the derivative at 0, 1 factorial, x minus 0, second derivative, 2 factorial, x minus 0 squared, etc. So we need to find derivatives of sine at 0. And we could say f of x is sine, f prime is cosine, second derivative is negative sine, third derivative negative cosine, fourth derivative is sine. And then we substitute a 0, c equals 0, or x equals 0, and we get sine of 0 is 0, cosine of 0 is 1, negative sine of 0, negative cosine of 0, sine of 0. And we'll substitute that into these. So f of 0 is 0. F prime is 1. So we'll get a 1x. The second derivative is 0, so that's all 0. And then the next one was f triple prime is negative 1, so we'll have a negative 1 over 3 factorial x cubed. And we can see a pattern here where we have the first degree, third degree, we would skip the fourth degree, and I'll write it down here. We have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and that keeps going. Just to write out the general term, we should write this so we can just see the pattern. It's alternating, so we can write that. And then we'll have x to an odd power over that same odd factorial, odd number factorial. And we can create odd numbers with 2n plus 1, 2n plus 1. Put a 0 there and we get 1. If we put a 1 there, we get 3. So it's 1, 3, 5. Here is the... So we write that as the series. And now let's see when it converges. So we'll do the ratio test. Copy everything, replace all the n's with an n plus 1. Then we're going to divide by this, or multiply by its reciprocal, so I'll put that on in the numerator. We don't need to write the negative because of absolute value. This is going to be 2n plus 2 plus 1, that's 2n plus 3. 2n plus 3 there. And down here we have a 2n plus 3 factorial. So now let's expand everything. That's gone. We have x to the 2n times x cubed. In the denominator we have 2n plus 3 times 2n plus 2 times 2n plus 1 all the way down to 1. In the numerator, 2n plus 1, 2n minus 1, all the way down to 1 factorials. X to the 2n times x to the 1. X to the 2n divides x to the 2n. Here we have 2n plus 1 factorial, and there's a 2n plus 1 factorial. And we also have a 3 minus 1, so that'll end up being a 2 there. So we have x squared over 2n plus 3 times 2n plus 2. There's nothing else left. And as n goes to infinity, no matter what number you put here, as n goes to infinity, the limit is 0. So that means no matter what value of x you have, the series will always converge. So the series converges for all real numbers. That means that this series, if we graphed it, will match the graph of sine exactly for all real numbers. All right. Find the power series for e to the x centered at 0. Pause the video. I won't write x minus 0, it's just x to the 1. And we need to have all the derivatives, so f of x is e to the x. F prime is e to the x. F double prime is e to the x. They're all the same, and they're all evaluated at 0, so they all have a value of 1. And we're going to have f of 0 is 1. F prime of 0 is 1 over 1. That's just x. F double prime of 0 is 1 over 2. And then we would keep going. F, the third derivative is 1 over 3 factorial x cubed. So, in order to generalize the term, we can look at that being a 1. So we have 1, 2, 3. We'll have 1 factorial. This could be x to the 0 over 0 factorial, and that lets us write n goes from 0 to infinity, x to the n over n factorial. And if we do the ratio test, we'll find out when it converges. When does the series converge to the function value? For which x's will that happen? And we have x to the n plus 1, n plus 1 factorial, n factorial, x to the n. x to the n times x times n minus 1 and n plus 1 times n minus 1 and then an x to the n. So x to the n cancels. N factorial cancels with n factorial. So x over n plus 1. And again, n is going to go to infinity. No matter what number x is, we'll always have it divided by infinity. So the limit is 0, and that means the series converges for all real numbers. All right, so now we don't want to have to do all those derivatives, and we just want to substitute into this series for sine. So we'll say we're going to just memorize this. And then we just substitute x squared. So instead of writing an x, we write x squared. You could write this as x squared minus x to the 6th, x to the 10th, 14th, but in order to write sigma notation, it would be easier just to write it in this form, where we'll have x squared to the 2n plus 1 over 2n plus 1 factorial, negative 1 to the n. And then we could expand that if we wanted to. Okay, pause the video and try that one. Just copy the series for e to the x and substitute. So we know that e to the x is 1 plus x squared over 2 factorial so that means e to the radical x 1 plus radical x squared radical x cubed can simplify that. And I'll just write 4 over 2. This would be a 2 over 2. Because then we can see 1, 2, 3, 4. And that'll help us write sigma notation. So we have x to the n over 2 over n factorial, and it even works for the first term because if we put a 0 there, we'll have x to the 0 is 1 over 0 factorial is 1. And we haven't seen this yet, but cosine of x is just going to be the even exponents. So we have and it alternates. So we have, instead of x cubed, we have x squared. Instead of x to the 5th, we have x to the 4th. Comparing it to sine. And now we can just substitute 2x. So we'll have 2x to the even power. All right, pause the video and try that one. Sine x is x minus x cubed over 3 factorial, x to the 5th over 5 factorial, x to the 7th over 7 factorial. And now we want to do x squared sine x. So we just multiply all of these by x squared. Two plus 3. 2 plus 5. 2 plus 7. We have an alternating series. We'll do -1 to the n and x to the odd power, but we have to increase by 2, so 2n plus 3. So that's odd factorials, still stays the same, but the exponent got moved up by 2. Normally we started at 1, now we're at 3. So if I just go 2n plus 3, when we put a 0 in there, it'll have a exponent of 3. We'll stop there.